Hello everyone. This is the video lecture for Calculus 1 section 4.7 optimization. And there's no getting around it. This is a very long section. But it has a lot of cool stuff in it, honestly. It's really a good section. Lots of good word problems. I know, right? What are we going to be doing? We're going to find the min and the max. Min or max, depending on what the problem is, okay? And that's what we're doing. So here we go. So I got 30,000 square centimeters of material for a square base. Okay. With an open top. It's kind of like a box, just with an open top there. What's the largest volume? Okay. Well, you know what I like to do? I like to draw a picture. So I'm going to draw a picture, and it says it has a square base, so I'm trying to make it square here. There's your square base. And so basically we have some kind of X here, and then we have a height. I don't know, let's call it Y. Now, the box is empty. Well, it has an open top, so it's empty basically. And I'm trying to find out what volume could I put into this thing. That's a good question. So volume would be x squared y. The reason being is because you got x times y. So there you go. And this is going to be my maximum. My surface area is going to be the base and then 4 sides. So x squared is my base, x times x, and then I have 4x times y's. And that's going to be like each one of these sides. And there's 4 of them. There's no top. And this is equal to 30,000. Go, figure it out. And this is basically what every problem will be in this section. It'll be draw a picture, understand what they're trying to say and ask for, set up some equations, always almost a system of equations, and then you plug one in, solve for the other, etc., etc. So what if I solve for y? That's not too bad. So I'm going to move this over and divide, and so I got y is equal to 30,000 minus x squared over 4x. I'm going to take this and I'm going to plug it in right there. So my volume then is x squared times all this stuff. And then it's equal to my max. Well, again, I don't have like an actual number here for the volume. That's what the answer is. We're going to figure that out later. But right now, I would need to figure out like what is x and all that kind of stuff. So what we do is we go v prime, and we're going to take the derivative of this, and we're going to set it equal to 0. So that I don't have to go and actually make this into a product rule of sorts. I'm going to distribute my x squares. And I think, here, I'm going to do a couple things, actually. So I got 30,000x squared minus x to the 4th all over 4x. What if I cancel one of these x's? And then I can move this 1/4 to the front, along with the 30,000, not the 30,000. There's a minus sign, you can't do that. So this is still v. So I got 1/4 times all this stuff here. 30,000 x minus x cubed. And so that's, again, my max. Now I want to take a derivative. Notice that what I did is I simplified it because that's junky. This is much better. So the 1/4 stays, and then we just take derivatives here. So we got 30,000 minus 3x squared. And, again, when I'm trying to find my min or max, I'm going to say my derivative is equal to 0. Solve for x. We don't need this guy. If I move this to the other side, 3x squared is equal to 30,000. Divide by the 3 and square root it. I guess that would be 10,000, right? So the square root of 10,000 is actually just equal to 100. So that's my x. My y then, if you go back, there's a formula for it. It's right there. Actually, you know what? We don't need to do that. Let's just go right here. So that's my volume, right? That's what they're actually looking for. And so it's all in terms of x, so I guess I could just plug it in there. So 30,000 times 100 minus the 100 cubed. And blah, 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 blah. And I got 500,000 cubic centimeters. And there you go. I did mine a little bit different, but in the end, it's all about the same. Okay, 47007. It says I have a rectangle. They want to find the dimensions of it, and the perimeter is 76 meters. You want the area to be the largest. So the area is a maximum. Find the dimensions, basically the length and the width and all that. So this is an X and a Y, and that's what we're looking for here. You know what's funny is that if you're going to maximize your area, do you know what kind of rectangle you should have? If there's no other particular constraints, you need a square. Yep, you need a square. Let me tell you that there's certain shapes that are better than others that we look towards. So squares maximize area, given just some kind of perimeter. A circle, I believe it minimizes the surface area, kind of. There's a lot of other things out there, but like squares and circles and a couple triangles are just the answer. On my notes, I went through this whole big thing about how to go and solve and everything like that. You're looking for a square here. Okay, if they have another question that has a little bit more detail, I'll go and do it. But right now, it's just a square. So let's just, here, in fact, that whole thing's wrong. Let's just say it's x and x. So my area is x squared. My perimeter is 4x, and that's equal to 76. I don't even think I need this. And so if I divide by the 4, I get 19. And that's actually your answer in WebAssign. They want you to put a 19, comma, 19. I know this is just really weird. This is WebAssign. They want it in that format. That's whatever, I guess. So there you go. 19, 19. Two sides. Yeah. Okay. Next one. There's a ton of words here. I'm going to try to summarize as best I can. So, oh gosh, there's two boats, and let's just put it. I'm going to draw the picture. So we have a dock, and then we have boat 1 and boat 2. Why did I use 1 and 2 instead of A and B? I don't know. So we have, let's say, boat A, and it's going south at 20 kilometers per hour. Okay. And then we have another boat, B, coming into the dock at 15 kilometers per hour. Okay. The distance of the B boat is going to be an X, and the distance of the Y boat is going to be, or the A boat is going to be a Y, obviously X and Y. And I'm looking for the distance between them. So that would be a distance formula there. And so they give us all this words here. I basically just told you as it is. Okay, that's fine. So how many minutes until they are closest together? From basically their starting positions, how many minutes until they're the closest together? So in a way here, do they have a distance, an absolute distance? I don't particularly see anything particular. We're going to have to figure that one out. Anyways, I know. I'm sorry. Let me go ahead and tell you. The X naught, like my original, whenever you read all these words, something about reaching the dock within an hour. So I believe that X itself is 15. Yeah, is 15 kilometers to start with. So they want to minimize the distance, D, and go ahead and figure it out. So basically, at the initial amount, we got, let me make that a little bit bigger. We got an A, oops, and we got a B, and they are technically 15 kilometers from one another. Now, this one's coming closer, but this one's starting to leave. is that, and that's the initial time, is that when they're closest? Can they be closer? What about when the boat is somewhere like right here? Do we have a closer distance? What if like the boat is way down here and this dude's been sitting at the dock for a while now? Obviously, that is not the minimum distance, and so it's got to be sometime pretty darn close, and that's going to be the goal. Okay, so how do we find this d? Well, d squared is equal to x squared plus y squared. And then let's pause here. Okay, let's pause. This is the trick that you need to know about this problem and other problems like it. You do not want to say d is the square root of x squared plus y squared. This is incorrect. I mean, it's correct. It's just going to be a bad way to go about doing this problem. You're going to hate doing this problem this way. Honestly, it's just way too much effort. Don't do it. There's a beauty to being able to use implicit differentiation with this one here instead of always having to go straight with just find a derivative. So this one's going to be way better for you. Let's actually take this derivative implicitly, and maybe I can find my minimum distance. Okay, so basically the 2 comes to the front, d, and then we got d prime, right? This guy, if you remember from my other lectures, is my flag, and I'm just flagging it, saying, hey, I took a derivative with d. I know that looks weird, but that's what it is. Same thing here, 2x x prime. Again, there's my flag. And then I got plus 2y y prime. Again, I have a flag. They're just flags. They're just hanging out. And those flags actually are meaningful in some way or another. Okay, so let's talk about what they represent. This d prime here is what I'm actually wanting to set equal to 0 to find my minimum. I mean, that's the goal here. D by itself is actually supposed to be that square root business, which is not very friendly, but we might have to resort to actually plugging that in. I'm looking at my notes. You got to plug it in here in a second, but you don't have to take a derivative of it, and that's the point here. X and Y are actual distances here, and what we're going to have to do in the end is we're going to have a bunch of X's and Y's, and we're going to have to kind of simplify those somehow. So let me just rewrite what we have as best as I got, okay? So we got this guy, d prime, and then we got the 2x, and what's x prime here? What is the change in x value? Well, if you go back, it's right here, but it's not just a 15, it's a negative 15. I'm making this x distance right here smaller, so I'm getting less and less. But my y is going to get bigger and bigger, and so this is going to be a positive 20 for my y prime. So that's actually what those guys are. You can actually just plug those in directly. I'd like to put a plus 20 just to say, look, guys, it's really a positive 20. And that's what I did on my notes, because I do this a lot of times with related rates and other things to show that it's definitely a positive here, okay? Definitely a positive. Okay. Well, we want d prime equals 0. So, well, you know what to do. I take all this stuff and divide it to the other side. And just hang out with me for a second here. I have my notes in front of me. Of course, I could just kind of look at them and see the next step, but I have an idea or two. And so I want to just look at this for a second. This is what we got, and this is supposed to be equal to 0. Okay, pause. I don't know what the bottom is going to result in, and it's scary, honestly. But the top is what actually makes things equal to 0. Okay, so I'm saying that I kind of can just get rid of my bottom. And then if I move this guy over, I got 40y is equal to 30x. And then, I don't know, divide by 30, I guess. So then x is equal to 40 over 30x. Or, I'm sorry, y. And so I got 4/3 here. 4/3 y. Okay. What? I mean, yeah. Woohoo! Well, now what? Right? And this is where we have to do a little bit of work. We have to think about things for a minute, okay? So what I did is I created a formula in terms of time. And so let's go back to our picture for a second. I mean, this is exactly why this is going to take forever on this section, because there's just so much good content for sure. Okay, so I want to make a formula for x in terms of time. Well, it started at 15, but then I'm getting rid of 15 for every hour that I'm out. Okay, so basically within the hour, he should have a 0x. My y, on the other hand, started at 0, but he's going to be increasing by 20 for every hour. I think if I just plug these directly in, I should be able to get something that I'll look at more. So 15 minus 15t is equal to 4/3 times 20t. Solve for t now. Now, if I just created these out of the blue here, that is completely correct. I tried to show you and I tried to tell you we started at 0, and then we went 20, and we're increasing 20 for every hour, and t's going to be basically 1 hour here in this case, within an hour. I started at 15 distance, but I'm getting less and less, and then I'll hit the dock at an hour. So if you put a 1 in there, 15 minus 15 is 0, and that's how they're making that formula, I guess. How I'm making that formula, I guess. So I need to get all my t's on one side. Let's move this guy over, I guess. And so I got 15. What's 4/3 times 20? I got 80/3. Why is my calculator doing that weirdness? So, it's okay. Children always playing with my calculator. Plus the 15. At least it's giving me an answer. That's good enough. Okay, and then I'm going to move it to the other side. And you don't need all this fraction action. But since we're here, and yeah, that's the same I got there. I got t is equal to 9/25, but they're not looking for that. They're looking for like decimals and stuff. And so that's going to be a 0.36 hours. Okay. There we go. We did it. That's the time that it took. Oh, yeah, I'm sorry. They want 22 minutes. Oh, what? So how do you get that? 0.36 times the 60 is 22. All right. Hey, well, it's technically 21.6, but they said whole number minutes, whatever. Okay. We got lots more to do, and well, that's okay, because it's fun. It is fun stuff. So this is the necklace problem. It's like a classic here. We got we're selling necklaces for $10 each. Okay. And we got 20 per day on average. And then you're going to increase the price. Increase the price by $1. But then you decrease sales by 2. So basically a -2 sales. So you go from 20 down to 18. And so that's kind of weird, isn't it? And part A says, find the demand function. Find the demand function. P of x is equal to what? Well, yeah, I don't know what that is, but we're just going to call that price, because that's exactly what they're looking for. It's price. With x is your units sold. All right, how do we do this thing? Well, we have a point at, and remember that x is units sold. X is my original, my independent variable, and so the units sold would be 20 because I had them at $10. We have another point, so let's call that point P. We got point Q that we only have 18 whenever we sell them for $11. And what you can do here is find a slope. Y2 minus Y1, X2 minus X1. Skip the math, and we get a -1/2 slope. And then I got Y minus Y1 is equal to M times X minus X1. And this is just a classic here. It's just a classic in terms of, everything. Move the 10 over, and that's your answer for P of X. It's going to be -1/2 X minus the 20, and then plus the 10. That's what you're typing into WebAssign for part A. Okay. And I didn't do any of this math on my paper. I just said, oh, slope, look, and you put it in. Yeah, that's fine. That's fine. Okay, so it says now, if the material for each necklace is $6, what's the selling price to maximize profit? To max profit. Okay, so basically everything we just did was worthless. Well, not really. Okay, so my price is still the same, but I'm looking now for profit. And so that's going to be my price minus, I don't know, materials. And so that would be my negative 1/2, x minus 20, plus the 10, all this stuff here, and then minus $6 for each unit. 6x, blah, 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 skip the math, and again, we get, why is this, okay, pause. We're really close. I mean, that's good. Everything's good there, except one small thing with the price. It's the price for each unit. This is the price per unit, and then I'm selling X amount of units. Okay, this is like your dollars that you put on the price tag, and then this is how many you actually sold for the day, and so this would be your total dollars in your little cash box or whatever. You don't just, okay, so you like sell a bracelet for $20, and so okay, and there's like, I don't know, 30 sales or something like that. So then how much money do you have at the end? Well, I only have $20. No, you don't. You have a lot more. You got like $600. So because you're multiplying. Now, still though, again, profit is going to be minus the materials, $6 again per unit. There's that units again. I just have forgotten that little guy right there. I was looking down at my answer like, that doesn't make sense. So it happens. Distribute this X, combine like terms, blah, blah, blah. Skip the math because it's just a lot. And well, we get this guy. And so remember that we're trying to minimize or maximize profit, one of those others. And so I'm going to say profit prime is equal to 0. And so I want to find the derivative of this guy. The 2 comes down and cancels negative x plus the 14 is equal to 0. And you can easily see that 14 is the units sold. You need to sell 14 necklaces each day. So what's the price? Well, thankfully, we have a formula. It's 1/2 x minus the 20 plus the 10. Plug that thing in, and so then we get 14 minus the 20. We make a 6 and blah, blah math, and it's $13. And so $13 necklaces, you sell 14 each day, and that's maximizing your profit. They don't know what the profit. They don't ask for what the profit is, but whatever. Good enough for me. Keep on moving. Next question: the Norman window problem. This is a classically hated problem by so many Calculus 1 students. The Norman window. Like, actually, I was talking to my other Calculus 2 class the other day, and they reminded me about the Norman window, and I did not bring it up. Okay, so we got a Norman window. It has like a little bit of extra business at the very top there. And so that's a semicircle. My radius here is going to be x over 2. This distance is an x, and this is a y. They don't tell you all of this. They don't tell you this. This is actually a pretty important part to making this whole problem work here. But there you go. And they say the perimeter of the window is 24 feet. And then they want to say solve for x. What's this distance down here? To maximize your area. I don't know why it would be important for a window to have a particular perimeter. I mean, in all actuality, there are things that are important with windows and perimeter, but I don't see the importance of having to have a fixed perimeter. But whatever, somebody said they wanted it, and so we're going to do it. What's the area of this thing? Well, it's equal to x times y, and then plus half of a pi r squared. Half of a pi times r squared. Okay, that's half of a circle. My perimeter, thankfully they gave it to me, was 24. But my perimeter will be a y, x, and then a y. So I'm going to say x plus 2y. And then we have half of a circle's arc length. Now that's half of a 2 pi r, because that's the circumference of a circle. So half of a 2 pi r. And again, r is the x over 2. Thankfully, these guys cancel. We still have another half there. This guy's going to be, like, way a lot. So I got 1/8 pi x squared. And that's going to be my area. And then my perimeter, just do this stuff over here. X plus 2y plus x times pi all over 2 is equal to 24. Okay, well, there you go, I guess. If we want to solve for y, you can start moving your x's over here and then divide by the 2. And so my y should be equal to 24 minus x minus pi over 2x all over 2. I can plug that in right, well, close, right there. And so x times, and this is interesting, what I'm going to do is factor out an x, leaving behind a 1 plus pi over 2, okay? That's important because I pulled out a negative x, technically, all over 2, so that was my y, plus 1/8 pi x squared, and this is my area. This is my maximum. And so you know what you need to do? You need to do this guy derivative equals 0. So what's the derivative? It's not as bad as it seems. In fact, I would say distribute this guy up here and get the 1/2 out of the way, because it is not quotient rule. It is not quotient rule. If you were to do quotient rule, it actually still works, sadly, but I would not be going down that road because it's far too lengthy for this process. Okay, so this is still my regular old area here. I haven't actually done anything yet. All right, so now my prime, here we go, derivative. 1/2 in the front, 24 minus, and then we got a 2, 1 plus pi over 2, and then x, and then plus the 2 comes down, 1/4 pi x, and this whole thing equals 0. Start moving things around. Lots and lots of moving around. Pi's flying all over the place. And your answer is 48 over pi plus 4. Whew. Well, there you go. Wow, that was amazing. Oh, I know what you're thinking. I know. 24. 48. Yes, yes. Divide by 2, maybe? I don't know. Yeah, I'm not going to say anything because I don't think that's actually a good way to go about doing that problem. And so, there you go. Have fun with that. I don't know. If you want to be daring and try different things, that's fine. At one point, I'm sure I have figured out some kind of formula for it. I don't know anymore. So, we have a rectangular container, again, without the lid. Okay. The volume is equal to 10 cubic meters. And the length of the base is twice the width. Huh? I have my base is $5. Oh, yes, it got worse. $5 per square meter, and my sides are $3 per square meter. And then it says, what's the minimum cost? What? Okay. Let's draw a picture. Always draw a picture. This is not the scale, but and it has an open top, so I guess there you go. Close enough. All right. This is an X and this is a 2X. That's that length base twice width thing. And then we have a height of Y. And we already know the volume. And we do know the volume. It's X times 2X times Y is supposedly equal to 10. And I guess you could say my cost, I would say surface area, but this is going to be a cost function instead. I'm going to say that the base here is that $5. So 5 times X times 2X. And then each side, there's this is actually going to be a little bit longer than you think. We got 2 small sides. And so that would be an X. Oh, hold on. 2 of these. They're $3 each. And that's an X times a Y. And then we've got 2, again, $3 each per square meter thing, of the long sides. 2X times your Y. And that cost is what we're supposed to minimize. All right, see you in 5 minutes. Maybe 10, I don't know. That's a lot. I'm going to solve for y by taking these and move it over. So y is equal to 10 over 2x squared, 5 over x squared. That's not very friendly, but it is going to be enough to go ahead and plug in. And, yep, that's what we're doing. So I got 10x squared plus 6x times the 5x squared, 5 over x squared. And then I got, that's going to be 6 times 2 is 12. X, again, times the 5 over x squared. And then, cool. And this is still equal to a minimum, because that's my cost. I can cancel a little bit, but it really is not as easy. It's not as nice, I guess, as you can think about it. These x's here cancel, those x's there cancel. Here I got a 30. There I got 60, I think. So I can add them together to make a 90. Did I do that? I did. I made a 90. So I got 10x squared plus 90 over x is still my minimum. It's my cost. And so I need to take a derivative of that. So cost prime. I got 20x. And this guy here, this is actually x to the negative 1. And so when you take a derivative, it does this guy. And just for purposes of speed, that's what happens. Okay, set it equal to 0 and solve for x. Move this guy over. I'm going to multiply by the x to the other sides, make an x cubed. Divide, and then the cube root of 9 over 2 yields about equal to 1.65096, and that was a length. That's like meters and stuff like that. Well, remember they want the actual cost in the end. And so if you go back to, let's do that one. That's a good one because it's just already in terms of x. And so I've got 10 times the cube root of 9 halves plus 90 over the cube root of 9 halves. And so what is this equal to? It ends up being 8T1, $81.77, and that's my minimum cost. Did you really think we're done? 4.7018. Here we go. I got a box with a square base and an open top. Oh my goodness. It's a popular theme today. And I've got a volume of 4,000. So why did I do this problem? It looks so similar. Minimize the materials needed. I guess I'm meaning like surface area. Yeah. I mean, sometimes I just wonder if I even should be drawing this for time's sake here. There you go. X, X, and a Y. And so, not my best drawing, but it'll work. So volume is x squared y is equal to 4,000. My surface area, which is what they're trying to minimize here, is going to be, I guess it's x squared plus 4xy. And again, this is going to be my minimum. Blah, blah, math. We've done this a lot already. I'm just going to go ahead and skip ahead. And so I got x is equal to 20, and then my y is equal to 10, and there you go. I'm just not going to do it. So we've already done that one a couple times. I don't know what I was thinking. Whatever. Next question. Did you think we were done? 47025. So this one's a strange one indeed, and I really like this problem. It's one of my favorites. It takes me way back to all the cool math that I was doing when I was younger. Because that's what I was doing when I was younger too. I was doing math. Did you know that? Were you doing math when you were younger? Oh, you are younger. Okay. So we have a point on the line, and so there's my line right there, and it wants to be the closest to the origin. Now, you know what's really cool is the origin is so easy to calculate. So we got this point P on a line, and this line here, I'm just going to make it up. It looks something like this. And there's your origin, and let's call that my point P right there. You can see that their distance is going to be that little guy right there. So I want to minimize that distance. So I'm going to say distance prime is equal to 0. Well, remember that d squared is x squared plus y squared. And that's not good enough. I mean, this is good, but it's not good enough. It's technically this guy right here, because that 0, 0 is the x2 minus x1 kind of stuff, but then it's 0, so you don't really have to calculate it all, and da-da-da-da-da. It makes it easier, and that's kind of the point here, so we could just use this. Also, you already have what y should be, and so I'm going to plug that in right now, okay? So I got x squared, and then I got a 2x plus 4 all squared. This right here is what I'm trying to minimize. You can minimize the square, and it's still minimizing the original. Pretty cool little feature there in Mathy land. 2dd prime is equal to 2x x prime. And that's the thing. I don't think you even need an x prime. In fact, I think this is going too far. Just pause. I'm going to just minimize the distance at all, okay? And so we're just going to take a derivative normally. There is a lot of little shortcut trick things that I'm doing to make this thing work. I'm just wanting to show you. I can't go into every single reason why, because it seriously would be too long. I'm already a very verbose talker here on these recordings. There's no way you're wanting any more than what I already provide. Right? Move it over, divide, and I got an x that's negative, but that makes sense. Okay, so I got negative 8 over 5, by the way. That makes sense according to the graph. Remember that we had this right here, and they're saying, what's the closest point? So it's somewhere over here in negative land. My y should be a positive, and so what I'm going to do is plug that into my y equals to 2x plus 4. Y equals 2, negative 8 over 5, plus the 4, blah, 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 and we get a positive 4/5, and that's cool. So my point is a negative 8 over 5, comma 4 over 5. That's my answer. Now, how does WebAssign want it? I cannot remember. Do they want you to type the point like that, or do they already have the parentheses and you just got to give the two answers here? I cannot remember, but either way is fine. You got the math, and that's the most important thing. Okay, I'm going to ask that same question. Did you think we were done? Well, my notes stop here, but we're not done. So here's the funny thing. I went through my notes, and I stopped here, and then I go on to the next section. going to do that for a couple pages. 4.9. I'll do that here in a few minutes here on the recordings. And that was fun and all. Woohoo. And then I kept going, and I have more pages, additional problems for 4.7 right here. And I guess, in a way, you could say these are by popular request because I didn't do them all. But these two, I think it's only 2 problems left, maybe 3. They're so bad that I didn't understand exactly what I was doing with them. And then I tried to do them, and I got them wrong so badly, I just crossed through it on my notes. I wish I could show you. It's just huge X's through all this stuff, and I finally got it after like the 3rd try. So I am going to make no promises from here forward. If this was enough for you, cool. If you want to stick around, great. I'm going to keep going. These are additional problems, but I hope that I get them right. I don't know. They're really confusing. Okay. And so you'd have to do them eventually anyways. At least maybe a little hint might be nice. They want the dimensions of a rectangle, and they want the largest area that is inscribed by an equilateral triangle. Equilateral triangle. Side L. I think we're solving for L or something like that. Did I even get an answer? It just stopped. I don't know if I got an answer. Anyways, so yeah, side L. I don't have anything boxed in, so normally I always box in the answer, but I didn't do anything here. I don't know. And I got an arrow. It's weird. Again, additional problems, kind of just whatever they are. One of the sides of the rectangle is along the base of the triangle. Okay, yeah. Let's draw a picture. So I don't know if they drew a picture or not. Equilateral triangle is something like this. That's going to be the best I can do. And they want a rectangle that's going to maximize the area on the inside. Now, this length here is L, and again, this is an L, and this is an L. I'm going to call this inside here an X. I don't like that. Hold on. This is an X. I'll do that. And then this is a Y here, okay? So I got an X and a Y for my rectangle. And because it's equilateral, they should be 60 degrees, 60 degrees, and 60 degrees. Okay. Find the maximum area. Go. How do we even get started? Well, I can tell you that the area formula is X times Y. That's a good start. Exactly. Okay, so we got to get some more equations going. What I did is I looked right here at this little triangle right here. So that's 60. This is a Y, and this is L minus X over 2? Yes. So L minus the X, but only want 1/2 of those. Yuck. And that's all I got for that triangle. I don't know what this hypotenuse thing is. But I can use tangent with that. So tangent of 60 is equal to Y is opposite, and then this L minus X all over 2 is my adjacent, unfortunately. And so what I got now is more of a relationship between X and Y, at least a little bit. And so I can start moving some stuff around. And tangent of 60 degrees, I'm trying to put this in my mind, square root 3. Yeah, we'll just call it that. So I've got 1/2 L minus X is equal to Y over the square root of 3. I don't know, put the 2 over there too, and that's going to be in the numerator. So that's 2 over the square root of 3. And then we got L minus X. And now what? I guess I could solve for X. So if I move this over and move the X over, and you could solve for Y as well. I mean, either way. On my paper, apparently I solved for Y. So I got like Y equals something or other. But you're going to need an X anyways. So my X is equal to L minus the 2 over square root 3Y. Let's hang on to that guy for a little bit. Now, remember that my area is X times Y. And so I can plug that guy in right here. So L minus 2 square root 3Y, all times Y, again, is my maximum. And then I want to take a derivative here in a second. So I got Ly minus 2 square root 3, y squared. And this is still a maximum. This is still my area. But what I want to do is A prime. And so, taking a derivative in terms of y, x, whatever you end up with. So I got an L as a constant. Don't get rid of that L. It's a constant here. The 2 is going to come down, I guess, as a 4 now. And then this is equal to 0. And what you get when you start solving for stuff, move the y over and move stuff over, y is equal to square root of 3 over 4 times L. Okay, so we got that. What you could do is then take this here and combine them together. And I got x is equal to L over 2. And again, these are nice. I don't know what the answer is looking for. Again, I didn't box it in. I just did this and I stopped. That was it. So if there's more to it, great. Go and find it. I don't know. I can't remember. Again, these are just additional problems. Yay. All right. Now, that was actually an easier one. The next one, I'm not kidding you, takes 3 pages. And I messed up 2 times. So it's just crazy. Okay, I have a right circular cylinder. Inscribed. Oh, that's probably the additional part, the inscribed stuff. In a cone, of all things, with a height of h and a base radius of r. See how it's kind of going up? I'm sorry. That's just my tilting here. What's the largest volume of the cylinder? Okay, first off, what are they talking about? Okay, well, this is how it's going down. We got a can, we got a soup can, and it's inside of this big triangle thing, this cone here. And so think of it kind of like a can and a party hat. You know, like you're going to a party and you got your little hats. I know nobody wears the hats like that anymore. My point is that you got a party hat, and that looks stupid. I'm moving on. So, sorry. You got a can and a party hat. What's the biggest can that'll fit in the party hat? There you go. I mean, this is the kind of math that you could show off at parties. That would be so fun. So the first thing that I tried was to convert this into a 2D image. And so I just said, well, let's just do a rectangle and stuff. Failure. Failure big time. Does not work. Do not try that method. Okay, turn the page. All right, so now we're in 3D land, and we got to figure something out. So this can here, let's call this height. Did they say H? They said that the cone has H. So this is a Y. This is an H. And for the radius of the cone, let's call that an X. But my radius of the cone, so that's the radius of the cylinder, sorry. The radius of the cone is an R. So now we got all our variables set up. I mean, I'm just trying different methods, and they're not working. But I do want to set something up here for you. Apparently, similar triangles might be a good thing. I don't really know. Here's what I'm trying to get at. What about this? You see that cone? So if I looked at just this top cone right here, the radius would be the same as the cylinder, which is an x, and this height here would be my height minus the y. Okay, so this cone is similar to that cone. Similar cones. Does that even work? I don't know. Let's try it. I mean, I got the answer another page or two later, and it's crazy. It's not like it's just 5 or something. So similar cones, I don't know. If that's the case, I'm going to say that h minus y over x is similar to, again, that's my height, and so that would be my regular h and then my r. So this is the small cone on the top, that's the big cone on the bottom. And nobody likes fractions, and so I'm going to do r and h minus y, and then I got hx and distribute. So rh minus ry is equal to hx. I don't know, solve for x. I mean, I'm just trying stuff out here. I mean, I went through this before the class, but it's just so much going on. And so I've got an x equals in terms of everything else. I don't know. Maybe that might be helpful. Great. Great job. Now what? What are we supposed to do? So let's now go down a road that I don't know if it'll actually work here or not. They want to maximize the volume of the cylinder, of the can. So my volume of the can is a pi r squared h. But this is an incorrect formula because we're using r and h for the cone. No. What we really want is the x and y for the cylinder. So it's just a variable misplacement. Use your x and y instead, and this is going to be the maximum. Maximize the volume of not the cone, but the cylinder. Okay, sweet. You know what I did? I got a huge cross through all this, like just scratch through it. I said, oh, I solved for x. Go ahead and just plug this in and start doing a bunch of math. And that did not work, so don't do that. I'm going to flip the page and look at what I really did here. Apparently I didn't solve for x as easily as I thought. I solved for y. So this is fine. But what I did instead is I solved for y instead, and it's pretty similar. We get y is equal to h minus hx over r, and I know that they look different, but I canceled my h's and blah blah blah. It makes it look a little bit better. I did a little bit of simplifying. So I have this guy, and apparently I got this guy. What if I take this y and plug it into this guy? Notice that it's going to be a little easier than having a square there. Not that what I was doing last time is not good, it's just that it was too much work. And you know my thoughts on that. Turn around, don't drown. So I'm suspecting that I'm going to plug this in like this, and this is still equal to a maximum because that's my volume of the cylinder now, given that we have some kind of height and radius and stuff like that. Okay, what we're really wanting, though, is my v prime equal to 0. So how do I get to that? What I'm going to do first off is distribute, and so not doing this yet, I have a pi hx squared minus h pi x cubed all over r. And what I would like to do, instead of writing it like that, is have it like this. And this is still equal to my maximum. I haven't actually done the derivative yet, but I wanted to have my x's out in the front. And so then my v prime is going to be much easier. The 2 comes down. 2 pi hx minus, the 3 comes down, 3h pi over r x squared, and this is equal to 0. So you know what's funny is that if you factor out an x from both of these terms, crazy math. You have one answer is x equal to 0, and then your other answer is x equals, I'll just go ahead and do the math for you, 4 pi over 27 r squared h. Guess which one of these is your answer? It's not 0. What you did here was you minimized your volume, and if you have a 0 radius for your can, you have minimized the amount that could go in there. To reach this, oh, hold on. Sorry, that was incorrect. What I got is a lot better than that. That's my answer. Should have looked at my notes a little bit better. Blah, 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 work, math, and I got 2/3 R. That's what I really have. I'm sorry. Now I plug it back in to find my volume, and that would be my pi x squared y. Plug this guy in, plug in my y's that I already had. So pi, and this is, I don't know, I solved a lot of stuff here. I got a y equals 1/3 h, plug that in, and so blah, blah, blah. My answer is the 4 pi over 27 r squared h. So always watch to the end. Apparently I got something wrong, but whatever. So additional problems are now complete. And we're doing the best we can. I've done a lot, and I hope that you're still with me. If not, sorry. So I guess you're not listening, though. Thank you very much, and have a great day.